Hi, welcome to the second day of ACC. My name is Ankit Goyal, and I'm a postdoctoral research fellow in the Aerospace Department at the University of Michigan. In this talk, I will present some experimental flight results obtained by augmenting a quadcopter autopilot with a data-driven learning technique. Before I start, I want to acknowledge all of my co-authors and collaborators at University of Michigan and MIT who contributed to this work. I also want to acknowledge ONR for funding this project. The objective of the work in this paper is the development of a learning autopilot. Specifically, our goal is to implement a learning technique for rapid autopilot prototyping and investigating the efficacy of RCAC to tune an autopilot in real time. RCAC here stands for retrospective cost adaptive control that I'll describe in a few moments. In this work, we modified the PX4 autopilot, which is a very well supported open source flight stack. For quadcopter control, PX4 has a PID-based fixed gain control system that we augmented with RCAC to enable learning in real time. Finally, we extensively tested the learning autopilot in simulation environment with JMapSim and with a real quadcopter. So the multi-copter control problem is actually a very well-studied problem. Several groups have researched various control architectures and control techniques for this problem. The state-of-the-art autopilots combine model-based control with the loop closure approach, where the outer loop tackles the position control problem and implements this control law shown here in the box to obtain an asymptotically stable position aerodynamics. And the inner loop tackles the attitude control problem and implements these two control laws to obtain asymptotically stable attitude and angular velocity aerodynamics. The loop closure approach requires that each successive loop bandwidth be at least 5 to 10 times larger in frequency, so that the commands generated by the previous loop are quickly realized by the inner loop. So the quadcopter autopilot basically consists of these two loops. The first loop, called the position controller, it generates the desired forces and operates at about 5 Hertz, and the inner loop generates the desired torques and operates at about 100 Hertz. In practice, the mass and the inertia are actually difficult to measure and they most likely are time varying. Therefore, in practice, these terms are actually replaced by PID-like terms. So looking at more details, the position control shown here in blue is implemented in 2 steps. The first controller is a P controller and the second controller is a PID controller. The output of the position controller is the desired force. The details to convert the desired force and the desired yaw into desired attitude are shown in the paper. The attitude controller shown in the green box is also implemented in 2 steps. The first controller is a nonlinear controller, but it is parametrized linearly by controller gains, so we call it a P controller. And the second controller is a PID controller. So the main challenge of this problem is tuning all of these gains in the autopilot, which can range from 18 to 27 scalar numbers depending on the chosen structures of these controllers. Now, instead of manually tuning these gains, we use the retrospective cost adaptive control algorithm to update these gains in real time using measured data. To do so, we modify the control architecture by adding an adaptive control in parallel to each of these fixed gain controllers. The advantage of this architecture is that we can switch off any of these RCAC controllers or the fixed gain controllers independently. So RCAC is a discrete time, model-free, data-driven method which is applicable to stabilization, command following, and disturbance rejection problem. It is described in a lot of detail in this Control System magazine paper from a few years back, and it was recently specialized for PID applications in this paper, which appeared, I think, last year in the Journal of Advanced Control Applications. So next, let me briefly describe RCAC before I present the experimental results. So suppose we have a system where we know the past inputs that are applied and a performance variable that is measured. A typical performance variable is the output error, and we want to drive the performance variable to 0. Our goal is to compute the control to be used in the future that will drive the performance variable to 0, of course. Although RCAC is quite flexible in the controller structure that it can optimize, we focus on the PID control structure, which can be written in the regressor form here. phi-k contains the measured data, and θ-k contains the PID gains, Kp, Ki, and Kd. Next, we define the retrospective performance by this expression, and by replacing the retrospective control by phi theta, we can write the retrospective performance as a linear function of controller gains. Sigma here is either plus or minus 1, and it usually is the sign of the first Markov parameter of the system. So now an efficient way of driving zk hat, which is the retrospective performance, to 0 is by minimizing the cost function, this cost function, which we call the retrospective cost. This cost function is quadratic in theta and is convex, which means its minimizer can be very efficiently computed using recursive least squares, and is in fact given by these two equations, these first two equations here. Once we compute the minimizer, we use it to generate the control at the next step, and that is all. That is all the retrospective cost adaptive control algorithm is. So we implemented this learning algorithm in parallel with all 4 of the fixed gain controllers of the autopilot. Now, both in simulation environment and the real quadcopter that we tested, the controller gains that are available in the PX4 flight stack are actually pretty well tuned. So to emphasize the performance of RCAC, we detuned the fixed gain controllers by multiplying all of the fixed gain controllers by a constant scalar alpha. This obviously degrades the closed loop performance of the autopilot. What we are hoping for is that RCAC will update the controller gains accordingly, such that the loss of performance because of the detuned controllers is minimized. Or in other words, we are hoping that RCAC will recover the ideal performance once the fixed gain controllers are degraded. So we first tested our hypothesis in a simulation environment. We flew a simple mission with 5 waypoints. The plot on the left here shows the top-down view of the trajectory flown by the quadcopter for alpha equals 1. Alpha equals 1 means that the fixed gain controller is actually well tuned, and we therefore get this red trajectory, which we consider as baseline. With alpha equals 1, RCAC actually doesn't do much since the performance is already good, and RCAC trajectory is shown here in blue, which lands almost on top of the red trajectory. Now, to degrade the performance, we set alpha equals 0.3, and this really degrades the drone quadcopter performance. Now the quadcopter is flying all over the place, as shown by the red trajectory in the plot on the right here. The RCAC trajectory, however, which is shown in blue in this plot, shows that we recover the baseline performance. So once we are confident with the desired, with the closed loop performance, once we are, let me start these videos. Once we were confident with the closed loop response with RCAC in the simulation environment, we tested the learning autopilot with a real quadcopter. The video on the left here shows the fixed gain controller where alpha equals 0.5. So the closed loop performance is obviously degraded. The video on the right shows the response with the learning autopilot where RCAC is updating all 4 adaptive controllers. The performance actually improves a lot and is very similar to the performance obtained with the well-tuned fixed gain autopilot. More videos of these flight tests are uploaded to YouTube, and you can find them by scanning this QR code shown at the top. Let's see. So the video on the top actually takes 2 minutes, and video on the right, which shows the adaptive autopilot, actually finishes the mission in half the time. On the left, the quadcopter is still making its way towards the end. Anyways, here is the data from the real flight tests. Solid lines on the left show the quadcopter trajectory without RCAC, and the dashed lines show the trajectories with RCAC. In the nominal condition, that is alpha equals 1, the fixed gain autopilot and the RCAC autopilot perform similarly. We consider this a baseline performance. With alpha equals 0.5, solid red, the solid red trace shows the fixed gain autopilot trajectory, whereas dashed red shows the RCAC autopilot trajectory. Clearly, RCAC recovers the baseline performance in this case. With alpha equals 0.3, the quadcopter actually does not take off with the fixed gain autopilot because the mission planner cancels the mission. This is due to the fact that the quadcopter doesn't take off in some pre-specified time. The dashed green trace shows the RCAC autopilot trajectory with alpha equals 0.3. Again, RCAC quickly learns and recovers the baseline performance. These plots on the right-hand side show the gains adapted by RCAC. As alpha is reduced, magnitude of these gains is increasing, showing that the RCAC is compensating for the degraded stock controller. So the take-home message from this work is that RCAC is a computationally inexpensive technique that can be used to learn controller gains on the fly. It can be used to tune gains automatically for a novel physical design without relying on tuning heuristics and expert knowledge. It can potentially improve the performance of a fixed gain controller. It can also potentially expand the operational envelope by adapting to changing dynamics, as is typical in the case of changing payloads or frame damages. Here are some relevant papers which cover the background material used in this work. And thank you so much for listening, and I would be very happy to answer any questions now.